Kita sambung dengan short circuit calculation, sample exercise. So tuan-tuan, you can either use per unit method ataupun MVA method. So let's see the question first. So only do part B1. Okay. Part A, describe two ways in which short circuit current in the power system may be limited. Is this one just for sharing lah. You can use a transformer with high impedance, but you'll lose on the load flow study, or the voltage drop will be higher. Or you can use modern technology like short circuit limiting reactors or IS limiters. So there are a few ways lah for you to limit short circuit. So now the question for this sample exercise is we want to focus on part B1. So we have figure Q4 here. Two 11 kV generators, you can see on the left and right side, feeding a 132 kV double circuit line through generator transformer. So each 132 kV line is 40 kilometers long and with an inductive reactance of 0.7 ohm kilo per kilometer. So calculate the current flowing in the fault and the contribution from each generator for a three-phase fault. So this is a balanced fault, three-phase fault. Anything other than three-phase fault, anything other than three-phase to ground fault is an unbalanced fault. So the only balanced fault is three-phase and three-phase to ground fault. Single phase, phase to phase, or phase to ground, that one are all unbalanced. So MVA method is usable only to answer for three-phase fault. Balanced fault. Three-phase and three-phase to ground. Okay. So we need to answer only point number 1, B1, point A on the bus bar close to the generator X. So this is the fault location here, point A. So let's take an Excel out. The answer is on the next few slides, but we will share with you. Let's do an Excel first, just to simplify our life. Excel. Okay. So we have here one generator. Okay. So let me simplify first the diagram. So you have your Gen X, then you have your transformer X, and then you have your bus. Your bus, okay. So bus bar, fault at A. Bus X, I call it. Alright. So then you have another one. Let me bring this down a little bit. So you have another. So Gen Y, transformer Y. Then Gen Y. And this is cable. Okay, so we do per unit first. So let's calculate. So we have two voltage level here, 11 kV and 132 kV. So let's set S base as 100 MVA. Well, the V11 and V132 base is 11 kV and 132 kV respectively. So you have V11. So what's the I base at 11? So let me bring this down a little bit. So I base 11 would just be in terms of KA rating. So this would be equal to your S base divided by square root 3 times the voltage level of your system. So that would be around 5.2489 kA lah. Okay. So the Z base at 11 would be equal to V squared over S, which is your voltage squared divided by your, divided by your 100 MVA. So that's 1.21 ohms. And we can repeat this same here. You can just copy paste. Sorry, can just copy paste here. So this is I base at 132 kV and I base at Z base at 132 kV. So these are our base ni lah, base calculation lah for the S base in voltage, current and so on lah. So what do we need to do first? Number one is what is the data given. So generator X is given as 125 MVA and the impedance is the X given as 25%, 28% or 0.28 lah. Okay, let me add another column just to let people have more clarity. Okay, so this is the S rating, this is the Z already. So I've converted from percentage into the normal value lah. Alright, so what's the S new? S per unit, sorry. The impedance in terms of Z per unit would be what? Hold on. So this is Z per unit in terms of the old base. So Z per unit new, Z old, this is per unit. So let's see the old formula. So remember this. Okay, so the Z new according to this is X% times S base over S meter lah, because our 11 we have selected our base 11 kV. So the generator is 11 kV, so there's no need to change the voltage. So we can just use this formula Z% times S base over S, the original S of the generator lah. So this would be equivalent to the old per unit times the new base, which is 100 divided by the old base. Okay, so it becomes 0.224 per unit. So we repeat in the same manner for transformer. So what's the old base of transformer? Is 125 MVA. So the Z old is 0.18 or 18%. So it automatically calculates for you lah. Alright, so we repeat again the same method for generator Y. Sorry, and transformer, I'll just copy first. So generator Y is 75 MVA, it's still 11 kV. So impedance is also 0.18, and the new impedance is 0.24 per unit. Whereas for transformer Y, it's 75 MVA. The old base is 12% or 0.12, and the new impedance is 0.16 per unit. So for cable, so cable is located at 132 kV side. So cable we have, it's a 40 kilometer length cable, 40 kilometer length, length 40 kilometer. So the resistance is how much per kilometer? 0.7 ohm per kilometer. Ohm per kilometer. So Z cable equals to Z cable equals to 40 times 0.7. So to change for cable, we just divide the Z of the cable over the Z base. So since we are using a 132 kV, the cable is at 132, so we use the Z base for 132 kV. So Z cable would be, so this one is 28 ohm. So equals to this one, 28 divided by the Z base, which is 174.24 ohm. We are selecting the one at 132 kV lah, because this cable is supplying the voltage at 132 kV. Okay. So now we've already converted all the impedances into this one. So now you need to imagine a little bit. So we have the generator source and the transformer and the cable along here. So is there something that I can use to draw? So we have here your generator. Oops, not too friendly. So let's do it in this manner. So generator X, then you have your transformer X, then you have your faulted bus, bus A. Then on looking from here, let's transpose all from the top. So from here you have your generator Y, transformer Y, and also cable 132 kV cable. Oh, I'm sorry. So this is for a single line cable. Since this cable is in parallel mode, so we can parallel this cable. So 40 kilometer 0.7 ohm is per cable. So this is for one cable. So Z cable parallel would be equals to times itself divided by itself plus or half of it. Okay, so that will be the Z cable in parallel. So this will be Z cable parallel. Alright, so if we can draw this like a box, just for you guys to imagine it. So we will have so what else we have here is this is the way that you should imagine lah. Huh? Okay, let's see what else do I need here. So you have this side here. So we've calculated the impedances for all of these components. So we need to simplify all the components with respect to this faulted bus. So in this case we have 0.224 ohms per unit. For the transformer we have 0.144 per unit. For this cable in parallel is 0.0803, 0.0349 per unit. Transformer Y is 0.16 per unit. Generator Y is 0.24 per unit. So these are impedances in terms of per unit. So for the one in series, we just add up, and since these two are in parallel, so these two we will sum up lah. So we'll do the simplification first. So once you add up, you will get what? 0.24. Let's see. You have this one plus with this one. Well, this one is a summation of these three components. So this is the value that you get. Okay, step 1, step 2. Sorry, this is step 2. So the faulted bus is still here. Faulted bus A. So this one you've already calculated. Okay. So these two are in parallel. So you just do the parallel. So finally, so step 3, this one would just be the parallel of two resistors times this one divided by this one plus this one. So this is the impedance. This is the impedance at point A per unit. Okay. So once you have gotten this per unit, so now it's just to calculate your I base I per unit for the short circuit level. So step 4, calculate the short circuit level at point A, which is still in per unit. So we always assume that the voltage per unit is 1.0. But if you're using IC 60909, they will recommend you at 1.05 for low voltage and 1.1 for the high voltage. So we use voltage per unit here is 1 per unit. So V 1 per unit. So current is just equals to V divided by Z. Alright, so what do you get here? You get 1 divided by this one. Equals to 1 divided by so this is per unit. So the I for A at 132 kV would be just the base current, the the per unit current times the base current, which is around this value lah. So let's see, times 4 point. So this will give you around 2 kA. So this is our calculated value lah, based on the per unit method. So this is your final reading. So this is step 0. Step 1. Okay. So this is our final value lah. This is the fault current at point A, 2 kA. So this is the per unit method. Let's try and use the MVA method, whether we get the same or almost the same answer. Okay, again I'm gonna be using the same concept here. Oops. Okay, so number 1, convert to MVA first. Okay, so for Gen X, your MVA given is 125 MVA. So for the transformer, it will be, let me put down here the formula for you guys. Okay. Okay, so we have here generator X. So for generator, it's just the MVA divided by its impedance in per unit. So in this case, our generator is 125 MVA and the impedance is 28%. So it's equals to 125 divided by 0.28. So that is for generator X. How about transformer X? Same method. It's 125 MVA divided by 0.18. And that is your MVA for the transformer. So what else? So cable. So cable, we will have 2 cables. 2 cables. So I will show you one by one. So this is just for one cable. One cable, just for one. So you have your impedance. So the cable is actually V squared over R or Z. So in our case here, our voltage of the cable is 132 kV divided by the impedance, which is 40 kilometers times 0.7 ohm per kilometer. And that is the cable impedance the cable MVA fault level for one cable. Alright, so this is for one cable. Just to note for you guys. Second is generator Y. You have 75 MVA and impedance 18%. So 75 divided by 0.18. And for transformer Y, this is transformer Y. Okay, transformer Y is 75 MVA divided by 0.12. So this is what you get. So this is equals to this one. This one is equals to this one. Oh, sorry. equals to this one. This one is equals to cable. Cable parallel means for cable in parallel, I will write down later. So we have a transformer Y and generator Y. Okay. So for cable, actually you have two cables in parallel. So never mind, we can calculate you the impedance of the cable in parallel to simplify. So for a cable in parallel, the impedance initially is 28 ohm. So since these two cables are in parallel, 28 ohm. So 40 times 0.7 is 28 ohm. So 28 parallel with 28 will become 14. So we will get about half of that cable. Oh, sorry. It's for half of that cable. For two cables. So this is the value that we are getting. So let's reduce that. Okay. So you have your faulted bus somewhere down here. So you have your so you need to reduce these two and these three. So these two are in series, so we do it like a resistor in parallel. So this one times this one divided by this one plus this one. Okay. Oh. So that is our value here. Where else for this one? I'm just going to use this. So by right, 1 over S equals to 1 over this plus 1 over this plus 1 over this lah. So I'm just going to simplify it further. It's going to be 1 over this one plus 1 over this one plus 1 over this one, and you're going to reciprocate it. So to the power of minus 1. And that will be your MVA. So that is the fault level. So since these two are in parallel, these two are in parallel, parallel. So you just add up both. Okay, so we'll repeat again the last step. So the final value would be equals to this one times this one divided by plus this one. Oh, times. So this is what you get, 100 MVA. So the I short circuit, So this is step 1, you convert to MVA. This is step 2, which is you reduce the MVA. Step 3, final MVA and calculate the short circuit. So based on this value of 170 MVA, so the I short circuit at point A would be equal to the apparent power fault level divided by the voltage. So in this case, our voltage is at 132 kV. So square root 3 times the voltage is 132 kV. So do we get the same answer? Oh no, we do not get the same answer. Okay. Hey, I'm sorry. These are in parallel. I made a mistake here. So we're just supposed to add it up. See? Okay, so it's supposed to be this one plus this one. Ta-da! Yes, and you get KA. So this is for the MVA method. I will post also this Excel sheet together. So PU method you get also 2.09911 kA. So MVA method is a little bit more straightforward and easier, but we must be careful in terms of paralleling and series MVA when you doing the reduction for the MVAs. So let's get back to the PowerPoint. So we got our answer just now is 2 kA. So this is per unit method already simplified for you. So we are getting around the same answer, 2099 kA. So we got around how much? We got around 2099 kA. So same value. Oops, sorry. This is based on per unit solution. So for the MVA method, we convert it first to MVA fault level for each of the transformer and cable. Okay, for one cable it's around 622 MVA. For two cables in parallel, it becomes like 20 km cable. Okay. So we also get 2099 amps. Sorry, this is supposed to be KA. 2K, sorry, this is correct 2000 amps. 2000 amps. So this is 2K. And with that, we finally end our long-awaited 17 series video series on protection and introduction. So if you guys like to listen to this electrical sharing, please share this with your electrical fraternity. Do subscribe to my YouTube channel. You can just search on YouTube Crux of EE, and also subscribe to my Facebook page Crux of EE, and also Instagram alias Crux of EE. So if you have any questions, just throw in the comments below. Or you can email me directly here. So please wait for more other electrical videos to be shared in the future, and thank you again.